briefly introduce the project to you, the 100K Tree project, and as Nina said, it's funded under the EU Space Program. This project, if you can maybe turn to the next slide, please, Alessandra. The purpose of the 100K Tree projects. Can you move to the next slide, please, Alessandra? Yes, and maybe put it in presentation mode. So our aim with the project has been to look at the cities across Europe and try to encourage tree planting based on some decision toolbox we have developed based on Copernicus and some modeling tools, and by use cases to demonstrate the usefulness of the project, and in particular looking at the ecosystem services of the trees. And what we have also been doing is to try to put a value on that in terms of monetary value on the impacts of planting trees. So the idea is by kind of providing these evidence-based business cases that we can encourage more tree planting in our cities. Next slide, please. So this is the consortium. So we are quite a small group, and it's not a huge project either. So as you can see, we are kind of evenly split across Europe with Danish partners, French and Belgian partners, and partners in Bulgaria. And we have two kind of test cities, which has been Copenhagen in Denmark and Sofia in Bulgaria. Please, next slide. So this is kind of our concept in a nutshell. So by developing these different toolboxes or different components, we've been looking a lot into trying to understand the user requirements from our cities. There's a crowd science app, as you will also see a demonstration of. There's been some of these products developed looking at tree maps and some automated spectral tree analysis. We have developed some enhancement tools based on Copernicus data. We have developed some standard tree types and described the tree attributes on these trees in terms of ecosystem services. And then we have built this model that can simulate different scenarios for how we plant trees and the impacts of that. And then we have been trying to look at these ecosystem services and have putting monetary value on each of the ecosystem services in order to be able to make some cost-benefit assessments of tree planting scenarios. And this has led to some of these business cases and hopefully some funding mechanism. So again, I mean, the focus on impacts has been really on the ecosystem services and for carbon, for air quality, and all the other ecosystem services tree are providing. And again, we have been trying to visualize the long-term impacts of turning some grey infrastructure into green infrastructure. Please, next slide. Next slide, please. So these are the services we have been working with. We might change a bit of the names as we move along, but so it's really some tree maps, tree inventory, change detection, the ecosystem service maps and hotspot identification, the economic valuation, but also trying to incorporate climate scenarios into the definition of future hotspots. And next slide, please. And these are the use cases we have been working on, 3 in Bulgaria, 3 in Sofia, and 3 use cases in Denmark. And you will hear more about the results of these use cases in the following presentations. So this is just a very brief introduction, and I hope you will enjoy the next presentations, which is more technical. So thank you very much.
Yes, sorry, but a bit delay. I'd like to introduce you to our next speaker, which is going to be Ali Islami. He's a PhD researcher from the Department of Water and Climate at the Free University of Brussels. And his research has been on numerical methods for assessing the urban environment services, assessing the environmental services of green infrastructure.
Hello, everyone. Can you hear me well?
Yes.
Okay. So I'm going to share my screen. Can you see my screen now?
Yes, we can.
Yes. Okay. So, hi everyone. Again, I'm Ali Islami. I've been 2 years into my PhD, and my research is about the environmental services of green infrastructure and specifically urban trees. So, for trees, we know that they provide a range of ecosystem services, and they don't only provide aesthetics in our cities. We have several ecosystem services, including stormwater management, biodiversity improvement, noise control, urban cooling, and air pollution removal. And for a decision maker to plant a tree, they have several options and several locations to plant a tree. For example, if a decision maker wants to manage the stormwater in a city, they can go for pocket parks as a type of tree planting scenario. And when they want to decide on the type of the tree, it can be either deciduous or evergreen. And when they are deciding where to plant, there are several options. So the problem here is that we know that trees provide several ecosystem services, but we have certain priorities in our cities, and it really depends on the areas of concern in a city. We know that environmental risks in urban environment aren't spatially homogeneous. We have some hotspots in a city in terms of pollution, in terms of noise, and in terms of flood mitigation. And at the same time, based on different types of trees and different types of green infrastructure, we will have a different range.
Ali, sorry, we missed your video or your slides now.
Can you see them now?
No.
No.
It's still connecting. Alessandra, I think it's best if you also present for me, because okay, so can we go to the second slide? Great. So as I was saying, the different range of ecosystem services and the decision on how to plant them, what to plant and where to plant gives us a lot of possibilities. And to decide on each of these criteria, we need some assessment tools to model which decision is the best. Can we go to the next slide? So in this project, what we technically do is to provide some spatially distributed maps for different environmental services. We identify the hotspots within urban environment, and we provide some opportunities for tree planting, because not everywhere can a tree be planted. It depends on the available space. And based on those available spaces and based on the scenarios, we will show the impact, and the output of that would be translated into monetary values. But we also need the integrated assessment, because these environmental services, we have different locations for each of them. And to optimize the decision, we will do multi-criteria analysis for the best outcome of tree planting scenarios. Can we go to the next slide? So for our modeling framework, we first deal with high resolution base maps of land cover and DSM and DTM. Based on that, we identify the urban canopy structure. And after that, we use the publicly available data on traffic, on meteorological data from Copernicus to show the hotspots in terms of different environmental services in a city and different problems that they might encounter. And based on the data on trees, we will have the final result of tree environmental services assigned to them for each single tree. Can we go to the next slide? For the use cases and some of the examples of 100K trees model, we had one local assessment of trees. It was to showcase that our model is able to capture the effect of single trees with small size. For that, we used the Roskilde schoolyard, and it was a parking lot which was aimed to be transformed into a green space using permeable grass grid and also small trees to minimize the soil excavation, for which we developed a scenario where we placed the trees, hypothetical trees, and we run the model for heat and flood to quantify how much change would this tree planting and intervention cause. And you can see some results of comparison of temperature in the baseline and the scenario after the implementation of trees in the two figures at the bottom. Next slide. And these results can be quantified into uh, absolute values, and we can use the information available for different cities based on thermal, for example, thermal comfort, to compare these scenarios and actually quantify how much would the impact of a number of trees or even one tree in particular. Uh, the graphs that you see on the right side of the slide, the one on top is the mitigation in runoff. And as you can see, trees provide a considerable change in surface runoff. But the problem in that area in terms of stormwater management isn't really considerable. But in terms of heat, comparing different scenarios and comparing the thermal comfort in Denmark, which is 24 degrees Celsius, we can see that trees can actually have a significant impact in regulating the temperature, up to 25% positive impact on average ambient temperature, and 50% positive impact in terms of local thermal comfort at the location of the tree, which is mainly due to shading. And for runoff reduction, the reduction was observed to be 75%. Next slide. These assessments can be also done in city scale. We have high resolution maps of air pollution, heat, and noise, which we use, again, the land cover data, the tree data sets, and DSM and DTM to identify the hotspots in terms of pollution, NO2, and PM 2.5 and PM 10. And also based on the traffic data, we can quantify the noise and the distribution of that within a city. This helps us to identify where is the hotspot for that specific environmental issue, and we can also assess the effect of trees if we have the data set of trees to see how much would one single tree impact the local ambient temperature. For example, you can see in the second figure, which for all the trees in the Lausanne Park in Sofia, we had one specific value assigned based on the local temperature and the average temperature in the whole domain. Next slide. And also for biodiversity and runoff control, we do assessments on the landscape within a city or in a specific area or district based on the biodiversity suitability index. The concept of biodiversity is pretty much complex. It can include humans as well. It can include flora and fauna, but for this project, we aimed for biodiversity suitability for birds, which is based on human accessibility, soundscape, and traffic load, which really influences the presence of birds, and it is validated in the literature. And for runoff reduction, again, as it is dependent on tree size, leaf area index, and crown biomass, we can assign a specific storage capacity to single trees and show that. Next slide. But all these assessments that I showed you in the previous slides are stationary. So it's static and it's for one time frame. The truth is that a tree grows over its lifespan, and this growth can also be quantified, and the environmental services also grow as the tree grows. To take that into account, we have a tree growth model, which takes the observed attributes of tree data sets in cities, and based on the tree species or based on other attributes, we can predict the growth rate of the tree for future projections. And this is a showcase in Colding, which we did an assessment on how would the tree canopy coverage grow for the next 5 years. And for young trees, it was observed to be 7%, and the whole domain, it was increasing by 1%, about 1% in canopy growth. So these future scenarios can also be modeled in our ecosystem services modules, and they can be used for quantifying the future benefits of trees. Next slide. And these tools can be used for assessing the green axis within urban environment, and also support decision making in terms of greening initiatives. In one of our use cases in the city of Sofia, we had the My Green School initiative, which was aiming for tree planting in schools and kindergartens. And in these locations that are identified by the map, the figure on the left, we did some assessment of green access, public green access, by doing fraction analysis of publicly available land which is covered by tree canopy. And then we evaluated the environmental risks within those domains. If you click on the next, you can see here that in each of these study domains, which is 300 meters, we assessed the green axis around that school, and we quantified these different ES maps that we presented in the previous slides. And you can find a direct correlation. This tool can be used for supporting these greening initiatives within a city. Next slide. And also next, could you please click on next? So for the air pollution and other environmental services as well. This is a use case in Ama Boulevard in Copenhagen, where it was planned to plant more trees, but also consider the alternative solution as traffic reduction, for which we run two different scenarios of tree plantation and traffic control. And we quantified the impact of trees as well as the impact of traffic control over the domain air pollution concentration. And overall, we saw up to 0.3 microgram per cubic meter per year pollution absorbed by urban trees. And also in the scenario of reducing traffic load by 50%, we saw an average of 30% reduction in concentrations in the whole domain. But how can these be interpreted in terms of benefit, like monetary values? We have literature available about the cost associated to each of these environmental services, and having a tree-specific ecosystem service, we can actually quantify what is the benefit gained from planting this tree and maintaining this tree. To showcase the same study area, the boulevard in Copenhagen, the trees that you see that are denoted by dark red, they have more contribution in air pollution removal because they are placed in densely polluted locations. And they logically contribute more to air pollution removal by dry deposition. And having the unit prices for different types of pollution, we can actually quantify how much would be the reduction benefit of that specific tree. And there is a difference between a location where a tree is not really contributing to that specific environmental service, as you can see, like in the table below, for pink trees, that we have less monetary values assigned to because they contribute less, and we have higher values for trees that are well located. And having all these information, we can go to the next slide to see where exactly to plant new trees. We do this assessment by having some information about publicly available spaces within a city, the locations where we have space available as a combination of land cover, bare soil areas, and public spaces. And based on that, we can identify the location of potential tree planting initiatives. But to prioritize that, we combine that with different risk maps in city, and using an MCA, we can go to the next slide and obtain a priority map for three locations. Can we go to the next slide? The figure that you see here is based on the combined assessment of environmental services and the impact of trees and the hotspots within the city. So this map helps the user to decide where to plant a tree and where is it possible to gain more benefits compared to the investments needed in terms of environmental services. So the aim would be to plant environmental services informed trees in a city, with minimizing the costs and maximizing the profit. If you have any questions, I'd be happy to. Thanks.
Lina, we cannot hear you. No,
Still
no.
can't hear you. Yeah, I can take over. So I'm next up. Let me just see if I can share my screens here. Let's see if I can do this.
Can you hear me now?
Yes.
Yes.
Okay, sorry, I had to change microphones. Let me just introduce Matt, who will talk about the mapping that we did to enable all the modeling that Ali has just presented. And this is where we have linked to the Space Call and the European Space Programme. So Mads is a senior business development manager and project manager specializing in Earth observation. He holds 2 MSc degrees in geography and geoinformatics, and has a strong foundation in sustainable land use, natural resource management, and advanced geospatial technologies. He's worked on a lot of EO projects and developed new tools, translating complex satellite data into insights. Darvish, you unmuted. Can you please? Yeah, thank you. Okay, I'll hand over to Matt.
All right. Can you see my screen now? Yeah?
Yes.
All right. So far, so good. All right. So afternoon, everybody. As Nina said, my name is Mads. I work for DHI in Denmark, so with a Danish partner on this project. Our main focus one of the focuses of the project has, of course, been to feed the work that Ali just presented with relevant geospatial data. Our role in this project has been to use satellite imagery to serve that purpose, along with Eurosense, who's also been working more with the LiDAR data and citizen science concepts to develop the data sets needed to run these models. We've also worked with satellite data to develop some independent data sets, more of sort of independent surfaces outside the modeling regime. So I'm just going to present some of the concepts that we've been working on in the project so far. Yeah, and somebody please shout out if you can't see my slides all of a sudden like the rest. Yeah, until then, I'm just going to continue. So just a brief sort of overview of satellite imagery, just to set the scene. This is something we work with every day, and I realize many in this webinar may not necessarily be so familiar with the data sets we work with. So just to present some of the key data sources that we work with, here on the left you have Sentinel-2 data, which is a satellite from the European Space Agency Copernicus constellation. So this is more or less the best of the best free and open data we have access to today. So that's readily available in most European cities, and sort of with a new imagery recurring every 3 to 5 days. It has a native resolution of 10 meters in most of what we call the spectral bands. And then going to the right, you can see something like this Airbus Pleiade Neo imagery has a resolution of 30 centimeters, and that is pretty much as good as it gets today from commercial satellites. And this has really been sort of one of the main engines of this project because of the added details it provides. And then to the far right, you can see an aerial imagery. A lot of people on this call probably have access in their countries to some form of aerial imagery. We do in Denmark as well, but it's also just to compare how close we actually are from getting imagery from satellites today that mimic what we can get from aerial imagery. And so yeah, just a few examples. So from Sentinel-2, we can is really, of course, it's cost efficient, it's free and open. We get really rapid updates, so we can monitor large areas very efficiently. But of course, we can't necessarily dig into the details. So we can see clusters of trees, we can see park areas, we can see green areas, we can see the shapes of buildings and roads and these sort of more coarse level land cover elements. But we can't do proper sort of object detection of smaller objects. So that's why in this project we primarily relied on PLI-NEO imagery, because this allows us to really dig into the details of the urban environments. And of course, under this project, it has been mainly revolving about aspects related to trees. So individual tree detections. Of course, you can also map out specific rooftop elements. You can see roads and cars and different other objects. Yeah, this year actually a new satellite mission has been launched that provides 10 centimeter satellite imagery. So now we actually do soon have data available that's close to what we get from planes. So some of the things we've been working on, generally satellite data has brought application perspectives in urban settings, and we work a ton with it to do digital elevation models, monitor vegetation health. We can map out evapotranspiration and drought parameters, urban heat islands, and many different things. But as I said, this project, 100K Trees, has mainly revolved around aspects related to trees. So one of the first things we worked with was tree detection. That was one of the main input data sets for Ali's model. So knowing the location of trees in the urban landscape. And in Earth observation, canopy cover is quite a common parameter. So knowing the extent of the canopy cover in the urban domain is sort of it's a standard product. But knowing the location of those individual trees beneath that canopy cover is something relatively new and something we developed under the 100K Trees project. I'm not going to go into details with this methodology. I don't have time to do it. But basically, in overall terms, our approach has been to mimic what you do when you count the number of people in large crowds. So, for example, a concert, when you take a picture there, what you focus on is really the mass and the density of people, and then you use those densities to try and estimate the number of people from that. And it's sort of a parallel to that approach that we've been used to be able to map out where do we have the individual trees in the urban landscape. So we've been working on the same case studies that Ali just presented in Copenhagen, Kolding, Roskilde, and Sofia. And this is an example from Copenhagen, one of the first examples we did. So it does look like a canopy cover map to your left, but actually it is a tree inventory with the location of all trees in Copenhagen. As you can see to your right here, an example of performance. It performs really well in most cases, particularly when you have trees that are relatively sort of spread out and evenly located in this example. Of course, when you have more dense forest areas and park areas where you have canopy covers underneath the main canopy cover, it's more difficult. But generally, street trees, sort of evenly distributed tree planting areas like this, the algorithm performs really, really well. And with that, we're able to calculate all the trees in an entire city. And of course, with satellite data, we can keep that updated annually or as often as needed. An example for Roskilde here, just another way of presenting the same data set, really. But again, the key is here to transform it more into this grid structure. We can sort of highlight so this is Roskilde, we can highlight the areas where you have more dense tree cover and where you have more sparsely density of tree cover. Of course, that reflects very much sort of the density of the urban structure. But as Ali just presented, this also gives you some insights and indication on where you should prioritize your tree planting efforts. Building on this, one of the key things we've also been working on is more of a standalone product under this project, mapping out what's called the 3-30-300 rule. So this is a relatively new concept developed by Cecil Korean-Gig about 4 years ago, and it aims to capture access to greenness in urban environments in a relatively simple and standardized metric. So basically the concept goes, and many of you have probably heard about it, that each citizen should be able to see 3 trees from their home. They should live in an area with at least 30% tree cover, and they should have at the most 300 meters to the nearest usable green space of a certain quality. So using the tree inventory we've been working with along with building footprints and geospatial data sets on green areas, we've developed an approach to map out the 3-30-300 rule again at scale, so at city level or municipality level, regional level, even national level. We should be able to do this now. And so, yeah, a few examples here from Roskilde. Again, what you have highlighted here in yellow in the upper right corner is the school that Ali just talked about. But again, the key here is really that we at building level now can get these metrics of access to green areas and visibility of greenness and high quality trees from residential areas. That gives you this detailed metric of greenness and quality of life and mental well-being related to access to trees and green areas. What we've done in our approach is more dynamic actually than the actual approach used, which is more binary. So that's more like, can you see 3 trees or not? We have made more of a dynamic scale. So from 1 to 10 aims to capture also the diversity of trees. So how tall are they? How close are they to your actual house? And how many are there? So it captures more of a dynamic range that you can use to specify your distinct metric in your urban area. So the same for 30 rule here. 30% canopy cover is actually quite a tall target. So most cities will not perform very well in this metric, which is also what you can see for Roskilde here. And then, the 300 rule, are you within or outside 300 meters of your nearest area? And then we compiled that also into a total score where we just weighted each parameter 30% and then compiled them into again a dynamic score of 1 to 10, telling you something about sort of the collective scoring of all 3 parameters for all passes in the city. And the last thing I just want to quickly highlight is another tool that we've built. We call it FRAME, Fine Resolution AI Mapping for Urban Environments. And this is the tool where we really use the Copernicus Sentinel data in an easy-to-use platform, allowing users to do their own land cover classifications. One of the key things is that we've built in this super resolution workflow. So basically super resolving the Sentinel-2 data from 10 to 5 meters without degrading the spectral quality of the data or creating hallucinations, which is quite common with these workflows. But basically it just sharpens the Sentinel-2 data, allowing us to make a more visually appealing and good land cover classification. Time is running by, so I just want to say this quickly. This will be released this summer, and it's quite an easy-to-use platform where the user can just go in, select their city, create a base map, land cover map, like you're seeing down to the right, and then create their own training data, either upload their own GeoJSON files or shape files to with their training data, or they can draw it directly in the platform to optimize this base map to fine tune it to the local conditions. Yeah, that's what we call human in the loop. Kind of go quickly by that, and then some insights into the results here. So to the left, where you can expect from the basic Sentinel-2 type resolution, and then the results you can get from this one. Again, just providing a little bit more refined and accurate outline of buildings and park areas and roads and these things, and water bodies. So that's all for me. Thank you very much.
Thanks a lot, Mads. Moving on, we've only got 10 minutes left, so let's try and fill it in. The next speaker will be Simeon Malinov, who is part of One Tree Foundation, and he has a background in landscape and architecture and urban planning. In the project, One Tree Foundation is leading the citizen science or crowd science application and the functionalities that go with that. And I'll ask Simeon to present that now.
Yes, thank you, Nina. I will share my screen. And I'll try to keep it as brief as possible. Can you just confirm if you see my screen?
Yes.
Yes. Okay. So, yeah. So as Nina told you, One Tree is a foundation that focuses on citizen participation, and particularly citizen science in urban tree mapping. But just to give you some context about why this is important. So what Matt showed you previously, and also Ali, are very effective ways of gaining information based on what we call distant methods. So those are not direct approaches of getting data. You can get it from images, you can get it from analysis, all sorts of data. But while those methods are very effective and very cost effective, they limit you to a certain amount of knowledge about what's going actually on the ground. So that's where our efforts come into the project. Just to give you some context, in Sofia, there's 1 million. That's an approximation. There's 1.5 million trees. And in our platform, just by now, there's 30,000 trees. That's one of the reasons why we want to engage citizens in this effort. Just so you can imagine of only giving this to the public authorities, or to the experts to map all of those trees on the ground. You can imagine yourselves what a vast job this is. So that's where the citizens come. And how do they do it? Through our web-based app. So one of the core functionalities of the 100K Trees project is this web application that we have developed for field work, basically. It's a mobile app that works on any device, and you don't need any installation at all. But I won't get that much into the technical aspects of it. It's a pretty simple process, and I will brief you in two very short videos after this presentation, where you can see how the actual process of mapping a tree goes. But it's basically in 5 simple steps. So you have a base map, you position yourself in this map using your GPS, you find the tree and you put it into the map. Then you take a photo of the tree. Then, if you can, determine the species of this tree, which is very important. Then the biometry, so this is where the tree actually becomes a 3D object. So we have the height of the tree, the stem, the crown diameter, and the stem diameter. So that's where the tree actually gets its proportions. It becomes 3-dimensional. And then you get some characteristics, if you can, of course. So those are all data that are mostly impossible to get from satellite images, let's say. And how do we do that? We actually organize those citizen science events where we have tree experts who work with citizens to educate them and show them the process and the whole point of mapping trees in the first place. So we gather citizens, we try to educate them, we show them the process, and it has proven to be a very effective method, because after a couple of minutes of education, citizens can already do the tree mapping by themselves. So that has proven very fruitful. And of course, there are some very enthusiastic citizens who would like to go deeper, would like to know how to distinguish species, for example, or some tree characteristics. But in general, the most important data is the location of the trees, the size of the tree, and if it has some damages or characteristics. Here are some photos from citizen science events. Those events are really cool because you get to explain to people why trees are important in the first place. And believe it or not, that's something that it's sometimes needed to be repeated over and over again, because it's not always obvious. Also, we support local communities. We work with local communities. Here are some screenshots of our app being used to map bird feeders. We have done that, and that also has proven very, very effective, because, of course, we do not limit ourselves to only trees, because urban ecosystems contain more than just trees. And you can also work on our app from a desktop computer, tablet, laptop, whatever you want, but it's optimized for mobile use, so from your mobile phone, regardless of the operational system. And now I'm going to play you two videos, and I'm going to walk you through what a tree mapping is. They're both under a minute, I think, so we will be pretty brief. Can you see the video loading? Just someone can confirm that the video is visible.
Yes.
So yeah. So as you can see, here's our app. The first task is to find the tree, locate the tree. If it's a deciduous or a conifer tree, position it more precisely based on the references of buildings, streets, other urban architecture. You add the tree, then you take the photo of the tree, which is one of the most important steps to actually prove that there is a tree there. Here you can see the photo being taken, and now that's saved into the system. The next part is getting the biometry of the tree. As I told you, this is very important, and most people can determine that pretty easily. It's not rocket science. Of course, it's all relative, but trees are very, very complicated shapes, so that's relative, but it gives you an idea of what the tree is. So the crown diameter is also very important, so you can know what the canopy is. The stem type, if it's single, if it's slow branching, or more. So that's the first part. That's the most important part, probably. The second part is more when you get into the specifics of the trees. So after doing the biometry, you get all of the characteristics. So we have a huge database of damages, characteristics, stuff that are important for, let's say, governing bodies, so people who care about the trees, and they would know if there's any maintenance. Here you can see some dry branches being added to the tree, which could be an indicator for some sort of a problem, health problem. Then you can add all sorts of, if you have horizontal branches, metal objects into the tree. If the tree has root sprouts, this is an indicator, of course, of some sort of a problem sometimes, that maybe someone needs to do something about it. And that is basically it. You can dig very deeply into the tree knowledge, but as you can see, the tree receives sort of a passport, sort of an identity, where all of the attributes are added in a specified way, but also you can add photos to every single attribute, which gives us a lot more information to it. So that's basically it. That's the One Tree app comes in hand into the 100K tree project, where all other data is insufficient, or all other data needs validation on the field. That's where our app comes from, and that's how we try to engage citizens through. So thank you.
Thank you very much, Simeon. I'm afraid that's been a very fast run through of what we've done in the project. So do we have, and we've got Couple of seconds left for questions. Are there any questions? There's also another way. If you go to our website, I'm just posting the website now. You can also ask questions via the website. If you go to our website and you follow the Get in Touch link. I don't see any questions coming up on the chat. I'll just give you a few more seconds for that. In the meantime, I'll thank our speakers for presenting the excellent work they have done. And I would encourage you to go and have a look at our website to get more information on the subjects that have been presented, and to get in touch with us and ask any questions you might have. I think on that note, I'll close the webinar on time, or 1 minute to spare. And again, I'd like to thank you very much for your participation, and to JISC for the organization of this webinar. Thank you very much, and